The objective of this lecture is to continue the study of coplanar impulsive orbit transfer. Now this is part 2 of this study. So in part 1, the focus was on the introduction of the concept of an impulsive orbit transfer and the development of the basic two-impulse orbit transfer between coplanar circular orbits. And this transfer, this basic transfer, was called the Hohmann transfer. Now, in this lecture, the focus is going to be on an extension of the Hohmann transfer to 3 impulses. And this 3-impulse transfer is called the BiElliptic transfer. Now, as the name implies, it is a transfer that uses 2 elliptic transfer orbits. So the BiElliptic transfer it uses 2 elliptic transfer orbits. And in the process of using 2 elliptic transfer orbits, it also uses 3 impulses. Now we will refer to these 3 impulses as delta V1, delta V2, and delta V3. But the best way to start this is to actually look at a diagram of the BiElliptic transfer. Now, similar to the Hohmann transfer, it's a coplanar transfer, and it's going between 2 circular orbits. So here's the first circular orbit, and here's the second circular orbit. Now, in the process of, let's draw this a little bit better. In the process of doing this transfer, the first delta V, this is why it's called the BiElliptic transfer, the first delta V, which I'm going to refer to as delta V1I, puts you on a transfer ellipse So this is the first transfer orbit that is larger than the radius of the second orbit. And at that point, you actually apply a second delta V, delta V2, which puts you on a second elliptic transfer orbit, and that second elliptic transfer orbit is tangent to the larger orbit at the bottom of the diagram as shown. And then you apply a third delta V, and that third delta V is actually a retrograde delta V. I'll explain all these impulses as we actually go, and puts you into the final orbit. So the first delta V is applied at the first orbit, so it's applied a distance r1 away from the focus. Now, this intermediate apoapsis, which is shown here in the diagram and referred to up at the top as r sub I, this value corresponds to this elliptic transfer orbit. So this is the first elliptic transfer orbit. And Ri, which is this intermediate apoapsis, is chosen such that it's bigger than or equal to R2. That's the key, and that's what we're going to use in the rest of the study. And then after the second delta V is applied, it puts you on to a second elliptic transfer orbit. That second elliptic transfer orbit, as I said, is tangent to, has its periapsis such that it's equal to R2. Now, let's look at the details of how each of these impulses actually is employed and their magnitude, so we can get the total delta V for the BiElliptic transfer. So the first impulse, delta V1, so I'm going to work with magnitudes now. So delta V1, which is equal to the magnitude of delta V1, is such that we need to know the initial speed and the final speed. So this is equal to V1 plus minus V1 minus. So now let's figure out what these things are. Well, V1 minus is equal to the square root of mu over R1. That's the initial circular speed. V1 plus, given the fact that the intermediate apoapsis here is r sub I, this is equal to the square root of mu times the square root of 2 all divided by r1 minus 1 over a1. Well, what is a1? Well, a1 is the semi-major axis of this first elliptic transfer orbit. So it's equal to, I'm going to write it over here because I've got the first elliptic transfer orbit on the right. It's equal to r1 plus ri all divided by 2. And I'll go back and I'll put the other one on when it becomes the time to do so. So as a result, delta V1 is equal to, well, it's V1 plus minus V1 minus, so it's the square root of mu times the square root of 2 over R1 minus 2 over R1 plus R sub I. And then minus the square root of mu all divided by R1. So if I rearrange this in a manner similar to the way I worked with the Hohmann transfer, then this is equal to the square root of 2 times R1 plus Ri minus R1 all divided by R1 times R1 plus Ri minus the square root of mu all divided by R1, which then gives delta V1 is equal to, well, if I factor out the R1 out of the square root, I get the square root of mu all divided by R1, and then this is multiplied by the square root of, well, I just get Ri in the numerator with a 2, all divided by R1 plus Ri, minus the square root of mu, all divided by R1, which then simplifies to delta V1 is equal to the square root of mu over R1 times the square root of 2Ri, all divided by R1 plus Ri minus 1. So that's delta V1. Next, we're going to do delta V2. So next, delta V2 is equal to the magnitude of delta V2 I, which is equal to V2 plus minus V2 minus. Now, again, this is a posigrade delta V, as is the first delta V, because they both raise the size of the orbit. Now what we have to do is we have to figure out what these values are. Well, if you go back and look at the diagram, you'll see that the impulse delta V2 is applied a distance Ri away from the focus. So as a result, the location of that from the V's Viva equation has to be Ri. And it's also such that the pre-impulse velocity or speed is based on the first transfer orbit, while the post-impulse speed is based on the second transfer orbit. So let's be real careful with this, which is V2 minus is actually equal to the square root of mu times the square root of 2 all divided by Ri minus 1 over A1, because it's actually based on the first transfer orbit. V2 plus is equal to the square root of mu times the square root of 2 over Ri minus 1 over A2. Now I'm going to go back to this diagram and I'm going to put A2 on here. A2 is equal to, well, its periapsis is R2, its apoapsis is Ri, divided by 2, because remember, Ri is greater than or equal to R2, so that is the semi-major axis of the second transfer orbit. So now what we're going to do is we're going to use the fact that that's the semi-major axis, and we're going to get an expression for delta V2. So delta V2 is then equal to the square root of mu times the square root of 2 over Ri minus 2 all divided by R2 plus Ri minus the square root of mu times the square root of 2 over Ri minus 2 over R1 plus Ri. So if you see, I used each one of the semi-major axes in succession, R2 plus Ri and R1 plus Ri, and I have the difference between these two velocities as my delta V. So now let's actually simplify this. So this gives delta V2 is equal to the square root of mu, and again we just go through the same process where we put everything under a common denominator, and we get Ri times R2 plus Ri, and we get 2 times R2 plus Ri minus Ri. That's the first square root. And then the next one is the square root of mu times the square root, and we've got Ri times R1 plus Ri, and we have in the numerator 2 times R1 plus Ri minus Ri, which then gives delta V2 is equal to the square root of mu times the square root. We've got 2 R2 in this case, all divided by Ri times R2 plus Ri, minus the square root of mu times the square root of 2R1, all divided by Ri times R1 plus Ri, which gives delta V2 is equal to the square root of mu over Ri times the square root of 2R2 all divided by R2 plus Ri minus the square root of mu over Ri times the square root of 2R1 all divided by R1 plus Ri. So then we can write delta V2. You can see that you can factor out the square root of mu over Ri. So you get the square root of mu over Ri times the difference of the square root of 2R2 all divided by R2 plus Ri minus the square root of 2 R1 all divided by R1 plus Ri. So that takes care of the second impulse. Now the last impulse is a little bit trickier than the previous two impulses, because we have to get the order right. Because remember that delta V3 is equal to the magnitude of delta V3I. Now, in the previous two cases, you notice that we subtracted V plus. We took the difference V plus minus V minus. But in this particular case, it's not going to work that way, because that third impulse is actually a retrograde impulse, and we have to be real careful with the way we do it. So what we're going to do is, we know that we still have V plus and V minus, but we have to figure out which order in which we want to do the subtraction, because we need this to be positive, this delta V3 to be positive. So we know that V3 minus is equal to, so I'm going to leave this off. So I'm going to put here, just for sake of argument, it's going to be V3 plus minus V3 minus, but it's going to be the absolute value. So notice the absolute value there, okay? Because it has to be a positive number. So I'll deal with which order this is done in based on whether or not V3 plus is bigger or whether V3 minus is bigger. Well, V3 minus, if we go back and look at the diagram again, let's go back. I should always refer to this diagram because it's useful. It's applied a distance R2 away from the focus. So as a result, we know that and it's also on the second transfer orbit. So we know that V3 minus is going to equal the square root of mu times the square root of 2 over R2 minus 1 over A2, because we're on the second transfer ellipse. And V3 plus is equal to the square root of mu over R2. But let's manipulate this V3 minus a little bit, and then we'll do a few other things with it to figure out which order we actually need to apply this, whether we need to do V3 plus minus V3 minus or V3 minus minus V3 plus. So V3 minus can be rewritten this way. It's the square root of mu times the square root of 2 over R2 minus 2 over R2 plus Ri, which is equal to the square root of mu times the square root of 2 times R2 plus Ri minus R2, all divided by R2 times R2 plus Ri. Now that gives V3 minus is equal to the square root of mu times the square root, so we get 2Ri all divided by R2 times R2 plus Ri, which is equal to the square root of mu over R2 times the square root of 2Ri all divided by R2 plus Ri. So that's V3 minus. Now we see what V3 plus is. It's the square root of mu over R2. So now we have to figure out, well, which one of these is bigger? Is V3 minus bigger, or is V3 plus bigger? So the way we can actually figure that out is by starting with the following results. So we know that Ri has to be bigger than or equal to R2. That's the condition that we established at the beginning when we drew the diagram for the Holman transfer. That's this condition right here. We actually established that, and we said that that was what made the for the Bi-Elliptic transfer, not for the Holman transfer, for the Bi-Elliptic transfer. So we established that condition. So given that Ri has got to be greater than or equal to R2 for the Bi-Elliptic transfer, we know that if I suppose I take Ri and I add Ri to both sides, so I get R2 plus Ri. Well, that gives me 2Ri is greater than or equal to R2 plus Ri. Now suppose that I divide both sides. If you look at this expression for V3 minus, it's got an R2 times R2 plus Ri in the denominator. So suppose I divide by exactly that quantity. That means that R2Ri divided by R2 times R2 plus Ri has to be bigger than or equal to R2 plus Ri divided by R2 times R2 plus Ri. But that means that 2Ri has to be bigger than or equal to R2 times R2 plus Ri. Sorry, 2Ri divided by R2 times R2 plus Ri has to be bigger than or equal to 1 over R2. So you can see that the R2 plus Ri cancels out on the right-hand side. Now let's suppose I multiply through by mu. So I get mu times 2Ri all divided by R2 times R2 plus Ri has to be bigger than or equal to mu over R2. If I take one more step on this process, I wind up getting the square root of mu over R2 times the square root of 2Ri all divided by R2 plus Ri has to be bigger than or equal to the square root of mu over R2. Now, if you look at that last expression, you'll see that on the left-hand side, I have exactly V3 minus. And on the right-hand side, I have V3 plus. So therefore, V3 minus has to be bigger than or equal to V3 plus. So this is equal to V3 minus. I should write it this way. V3 minus is equal to that. And this is equal to V3 plus. So as a result, we now have the order for our delta V. We know that delta V3 has to equal V3 minus minus V3 plus. So that means we can write delta V3 in the following way, which is we have everything. We can just do it now, which is it's equal to the square root of mu over R2 times the square root of 2 Ri all divided by R2 times R2 plus Ri minus the square root of mu all divided by R2, which gives delta V3 is equal to the square root of mu over R2 times the square root, actually, back up one step here. This is just the square root of mu, square root of mu. So this gives the square root of mu over R2 times the square root of 2Ri all divided by R2 plus Ri minus 1 when we're all done simplifying that. So now we actually have the total delta V. So delta V for the Bi-Elliptic transfer is equal to delta V1 plus delta V2 plus delta V3. That's the total impulse. And now we can actually write the total impulse in the following way, which is that we're going to actually simplify this total impulse to be such that we're going to actually use two quantities. So recall from the Holman transfer that we had R is equal to R2 over R1. Also, we're going to define a new quantity, which is going to be S, which is going to be Ri divided by R2. Now, S, so the quantity S, is the ratio of the intermediate apoapsis radius to the radius of the terminal orbit. And of course, this assumes R2 is bigger than R1, which is what we've been assuming in this. We're going from a smaller orbit to a larger orbit. So, given that, let's see if we can actually write this delta V1. So we're going to write delta V bi-elliptic in terms of R and S. And we're also going to normalize delta V bi-elliptic by VC1, which is equal to the square root of mu over R1. So eventually we're going to do that as well. So we'll get there, but let's do each of these one at a time. So recall from earlier that delta V1 is equal to the square root of mu over R1 times the square root of 2Ri all divided by R1 plus Ri minus 1. Now that was actually obtained back at the beginning when we actually did delta V1. That's this result that we had from earlier. That's this result. So we can now use that to be able to get this in terms of R and S. So what we're going to do is we're going to divide the numerator and denominator of that fraction. Same way we did when we were dealing with the Holman transfer, we're going to divide this by R2. So we get 2Ri divided by R2, all divided by R1 divided by R2 plus Ri divided by R2, and then minus 1, which then gives delta V1 is equal to, well, we have the square root of mu over R1, and then you notice that Ri divided by R2, well, that's S, and R1 divided by R2 is 1 over R. So this is going to give us the square root of 2S all divided by 1 over R plus S minus 1, which gives delta V1 is equal to the square root of mu over R1 times the square root of 2RS all divided by 1 plus RS minus 1. So there's delta V1. Now we're going to do the same thing with delta V2. Now delta V2 is equal to, well, it's the square root of mu over Ri times the quantity, the square root of 2R2 all divided by R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri. And again, I'm going to do the same thing, except for now I want to get this in terms of square root of mu over R1. So I'm going to do a couple of things at the same time. First I'm going to do this. I'm going to take this fraction outside, the factor outside, and I'm going to write it this way. This is going to be the square root. I'm going to write it as the square root of mu over Ri times the following. I'm going to write it in terms of, it's going to be R1 divided by R1 and then times R2 divided by R2. Now, of course, that just multiplies by 1, so I haven't done anything there. But that's going to actually help me be able to figure out how to simplify the rest of this, which is, now what I'm going to do is I'm going to divide everything again through by R2. So if I divide everything through by R2, I get 2 R2 divided by R2, all divided by R2 divided by R2 plus Ri divided by R2 minus the square root of 2R1 divided by R2, all divided by R1 divided by R2 plus Ri divided by R2. So that allows me now to be able to rewrite this delta V2. Delta V2 is then going to equal, well, let's take a look at this expression. Now what I can do is I can rearrange that factor on the outside. So I can write it as the square root of mu over R1, and then I can write it in terms of, well, if I move everything over, I can write it as in terms of R1 over R2 and R2 over Ri. So I get times R1 divided by R2 times R2 divided by Ri. So that gives me everything on the outside. The inside winds up simplifying to the first fraction. I get 2 all divided by, well, I've got 1 plus, so you get 1 plus, you've got Ri over R2, so that gives me 1 plus S. So let's move this over a little bit so that it's a little bit easier to read. 1 plus S, and then I get minus the square root. So if you look back here, you've got R1 over R2, so that gives me 2 divided by R, all divided by 1 divided by R plus S. And that 1 divided by R is because, again, I have an R1 over R2. So this gives me delta V2 is equal to, I get the square root of mu over R1, and then R1 over R2 is 1 over R, and R2 over Ri is 1 over S. So I get the square root of 1 over Rs, and then I get the square root of 2 all divided by 1 plus S minus, now what I'm going to do is I'm going to multiply through by R in numerator and denominator in the second term, and I get the square root of 2 all divided by 1 plus Rs. So there's the second impulse. And again, you see it's written in terms of the square root of mu over R1, which is the way I want to write it. So finally, recall delta V3. So delta V3 is equal to the square root of mu over R2 times the square root of 2Ri all divided by R2 plus Ri. Let's make sure that's an I, minus 1, which is equal to the square root of mu. Now what I'm going to do is mu over R2 times R1 all divided by R1, because again I want to get this in terms of the square root of mu over R1, times the square root, and I've got 2Ri divided by R2 all divided by 1 plus Ri divided by R2 minus 1. So when I'm done with this expression, I get that delta V3 is equal to, so let's look at this, delta V3. I've got the square root of mu over r1. That's moving the r1 underneath the mu, and I've got times r1 over r2. Square root of r1 over r2. Times, now what have I got here? I've got the square root of 2s all divided by 1 plus s minus 1. So that takes care of everything inside. So now what I can do is I can write this as delta v3 is equal to the square root of mu over r1, and then I get the square root of 1 over r times the square root of 2s over 1 plus s minus 1, which can be rewritten as delta v3 is equal to the square root of mu over r1, and if I multiply through by the square root of 1 over r, I get the square root of 2s all divided by r plus rs minus the square root of 1 over r. So there's the full delta v. So now I have the full delta v bielliptic. So delta v bielliptic is equal to delta v1 plus delta v2 plus delta v3, which can be rewritten as delta v bielliptic is equal to the square root of mu over r1, because I got that as a common factor in everything, and I've got times the square root of 2rs all divided by 1 plus rs minus 1. That's the first delta v. Plus, I've got the square root of 1 over rs times the square root of 2 over 1 plus s minus the square root of 2 over 1 plus rs, and then I have plus this last term, which is the square root of 2s all divided by r plus rs minus the square root of 1 over r. So if I put that in parentheses also, just to remind myself that that's associated with the last delta v. So we can rewrite this. We've got delta v bielliptic. Now, we should note that the following, which is that we're going to divide by VC1. So we're going to notice something here. VC1 is actually equal to the square root of mu over R1. So as a result, we're going to normalize everything here by that quantity right there. So if I normalize by that, what I wind up with is everything goes away except for the square root of VC1, because I've put it in the denominator on the other side, and we wind up with the following result. We wind up with the square root of 2rs all divided by 1 plus rs minus 1. That's the first delta v, plus the square root of 1 over rs times the square root of 2 over 1 plus s minus the square root of 2 over 1 plus rs. That's the second delta v. And the third delta v is plus, I've got the square root of 2s all divided by r plus rs. Let's make that r a little bit clearer. Minus the square root of 1 over r. And that is the full delta v normalized by VC1 for the bielliptic transfer. And that gives you everything that you need to know about the bielliptic transfer. Now let's see what's going on here in terms of understanding the structure. Is you note that delta v bielliptic divided by VC1 is a function of r and s. So we can think of it in two different pieces, each of which can be sort of connected to make this bielliptic transfer is that suppose you're given, we are given R2 and R1. So that implies we know R is known. So as a result of it being known, we can now think of this family of, or these bielliptic transfers as being a family of transfers in terms of S. So given R, the bielliptic transfer is actually a family of transfers that depend upon S. So in other words, if we freeze R at some value, so we know the initial and final radii of the orbits, then there are an infinite number of bielliptic transfers that depend on the value S, because S ranges between, well, what can it range between? Well, since Ri has to be bigger than or equal to R2, it ranges between 1 and infinity. Let's write this 1 and infinity. So it can go all the way out to infinity. Now, clearly, in a realistic case, you cannot have the intermediate apoapsis be infinity. But we can actually work a little bit with this concept of infinity to come up with what's called a limiting case of the bielliptic transfer. So the limiting case of the bielliptic transfer works as follows. It's when Ri approaches infinity. So this is a limit that applies as Ri approaches infinity. So note that as Ri approaches infinity, S also approaches infinity, right? Because recall that S is equal to Ri over R2. So as a result, as Ri approaches infinity, so does S. So we can actually work with these delta V's now, and we can figure out what is the total delta V for S going to infinity. Well, this transfer, when S approaches infinity, this transfer is what's called a Bi-Parabolic transfer. And it's a limiting case of and is the limiting case of the bielliptic transfer for S approaching infinity. Now, to see what happens in the case when S approaches infinity, let's go back and let's look at these delta V's. So delta V1 divided by VC1 is equal to the square root of 2RS all divided by 1 plus RS minus 1. Delta V2 divided by VC1 is equal to the square root of 1 over RS times the square root of 2 over 1 plus S, 1 plus S, minus the square root of 2 over 1 plus RS. And then delta V3 over VC1 is equal to the square root of 2S over R plus RS minus the square root of 1 over R. So now we're going to rewrite these three delta V's in the following way. We're going to divide numerator and denominator in all three by S. So divide numerator and denominator in each fraction by s. So what that gives is that delta V1 divided by VC1 is going to equal, well, this one's going to equal the square root of 2r all divided by 1 over s plus r minus 1. Delta V2, again divided by VC1, is going to equal the square root of 1 over rs times the square root of 2 over s all divided by 1 over s plus 1 minus the square root of 2 over s all divided by 1 over s plus r. And then delta V3 divided by VC1 is going to equal the square root of 2 all divided by r over s plus r minus the square root of 1 over r. Now, take the limit as s approaches infinity of delta Vi over Vc1 for I equals 1, 2, and 3. We're going to do it for all three delta V's. So if you look at the first one, as s approaches infinity, 1 over s goes to 0. So you're just left with delta V1 over Vc1 is equal to the square root of 2 minus 1. That's all that's left when you do this. Delta V2 divided by Vc1 is equal to, well, as s approaches infinity, the numerators, they all go to 0. So 2 over s, the numerator goes to 0, and so does the second one, 2 over s, the numerator goes to 0. So this whole thing just goes to 0, which just gives you that delta V2 is equal to 0. And delta V3 divided by Vc1 is then equal to, well, again, if you look at s going to infinity, you get the square root of 2 over r minus the square root of 1 over r, which just gives you the square root of 1 over r times the square root of 2 minus 1. Now, these are the limiting cases. Remember, this is not the Bi-Elliptic transfer. This is the Bi-Parabolic transfer. So it's really important to understand that this is for the Bi-Parabolic transfer. So delta V for the Bi-Parabolic transfer divided by Vc1 is just equal to the square root of 2 minus 1 plus the square root of 1 over r times the square root of 2 minus 1. And of course, you can write this simply as the square root of 2 minus 1 times 1 plus the square root of 1 over r. So that's the limiting case. That's the Bi-Parabolic transfer. And in the cases where it actually is relevant, it works as follows, is that in reality, a Bi-Parabolic transfer is not possible, because it takes an infinite amount of time. Now, to see that it takes an infinite amount of time, this is what the Bi-Parabolic transfer looks like. So if you go all the way back to these impulses, you'll see that we said that the process was that you're making that intermediate apoapsis infinity. So that means that the outbound, or the first transfer orbit, is actually a parabola. So the first transfer orbit is parabolic for the biparabolic transfer. Well, that takes an infinite amount of time because you're on a parabola, so you're going out to infinity. So somewhere out here at infinity, you're applying delta v2I equals 0. That's a fictitious delta v because you can't actually do it, but because you can't wait an infinite amount of time to complete a transfer. Now, similarly, the second part of the transfer, which is an inbound parabola. So this is the second transfer orbit. Is parabolic for the biparabolic transfer. And again, given that the outbound orbit or the first transfer orbit it takes an infinite amount of time, clearly the inbound is also going to take an infinite amount of time because it's coming out from infinity. So you're basically delta v2 is applied at r equals infinity, which doesn't make any sense because you can't apply at r equals infinity anything realistic. So in reality, even though this is the issue, so realistically, a biparabolic transfer is approximated as a BiElliptic transfer with a large Ri. So in other words, if you go back to the case of the BiElliptic transfer, it just means that if the intermediate apoapsis is large, then what you're going to get is you're going to get something that's going to look as follows, is that here are your two circles, and you have an outbound ellipse, but this outbound ellipse has a really large Ri. So this is a very large Ri. And that's large. Which means that when you come back in on the inbound transfer orbit, this delta v that's applied up here, that delta v2, so this is your delta v2, is approximately 0. It's not exactly 0, but it's small. You can say it this way, it's small. So it can be neglected. So in the case where Ri is large, you just neglect delta v2I, which is the same thing as just saying delta v2 is approximately 0. And that's the same thing I have here. This is the same thing as equivalently saying delta v2 is approximately 0. They're the same thing. So that gives us a sort of a complete picture of what the three impulse transfer cases look like. So basically what we've done is we've constructed a 3-impulse transfer called the BiElliptic transfer, and analyzed the total delta V for this transfer. and then an approximation, or I should say an idealistic version called the Bi-Parabolic transfer was studied. The BiElliptic transfer and the BiParabolic transfer. And that pretty much summarizes the three impulse transfer, coplanar circle to circle transfer case for this lecture. And we will stop here, and in the next lectures we're going to start talking about non-coplanar orbit transfer.